Yeah,
Yeah, why do you stay up in the
hello. Yeah, thanks for
Yeah, no, because. Next year. Yeah. I know. Yeah, I wanted just to because I did some.
we lost more. I think they're so I was
Somehow I think everybody's trying to do that. Yes. Christian is telling me about the Christian house.
yeah, that's
This museum is just.
so how big there
That was interesting.
I don't know.
And that
And that we're big. Big. Oh.
No, no, no. আচ্ছা, আপনি ওখান থেকে এখানে কপি করেছেন আমার ইউএসবি থেকে? আমার ইউএসবি থেকে তো পাঠিয়েছিলাম। ও আচ্ছা আচ্ছা আচ্ছা, আপনার ফার্স্ট টকটা তো? হ্যাঁ হ্যাঁ হ্যাঁ, ওটা হয়ে গেছে, এটাই জিজ্ঞেস।
So good morning, welcome to the morning session. So in this session, we will be having 4 talks. Two will be 30 minutes in duration and 2 will be 15 minutes in duration. So the first talk is by Kedar Dambre, and he's going to talk about monomer microdation transitions.
This is the video. Okay. Yeah. So I'd like to begin by thanking the organizers for this invitation to advertise our work. I'm going to be talking about what I like to call monomer population. And it's a little bit hard to sort of define at the outset, but just have a little bit of patience and you'll see what I mean. And this is largely based on the work of Ritesh Bola, Shaunak Biswas, Muslim Islam, and Zaid Ansari, students from TIFR, all of them, when they did the work at least. And it was motivated by or inspired by some earlier work, which was part of the thesis of Sambuddha Sanyal, done in collaboration with Old Friend. Let me just spend 2 slides on the motivation. In this paper, we were trying to look at diluted graphene, when the orbital that contributes to the single band description of graphene is absent at some site due to substitution. And we noticed that there's a non-zero density in the thermodynamic limit of zero energy states that seem to be tied exactly to the zero of the chemical potential. That's the particle symmetric point. And we made a bunch of naive guesses for what these exact zero modes could be due to. And here's 2 examples of the kind of guesswork we were doing at that time. These open circles are impurities, and these black dots are where the wave function lives, and you can check just visually that both of them will give you an exact zero energy wave function for the tight binding model for graphene. This graphene lattice is now shown here in brick wall notation, but you should be able to translate in your mind and take a look. There's a key distinction. Can you get rid of that stop sharing thing? It's obscuring. There's a key distinction between these 2 pictures. This one, if you mess around with the bond amplitudes, the mixing amplitudes between orbitals, if there's some bond disorder, this one doesn't remain a zero mode, it gets wiped out, it gets lifted. That one, no matter what you do to the TIJs locally, you continue to get a zero energy, exact zero energy state. And if you view the connectivity, pattern of connectivity in a lattice to be its topology and the value of the connections to be the geometry, then you might want to call these topologically. That's the language at least we try. So then we try to think a bit more about, how to, what's a general way of thinking about it. And this is all we could really come up with at that time. Imagine there's a sort of a rare region of the sample, which has local sublattice impact. The honeycomb lattice is a bipartite lattice. A talks to B, B talks to A. A doesn't talk to A, right? So imagine there's a region of the lattice which has local sublattice invariance, but it's an atypical region in the sense that its site boundary, which I'm denoting by these B sites, is all, let us say, B type. And in spite of the site boundary being all B, if you look at the total number of A sites and the total number of B sites in this atypical region, including the boundary sites, by the way, you will find that the A sites are in an excess. This is atypical because the boundary is B and yet the A sites are in. Right? So if you had such a region, or its complement, which is RB, where the B is in an excess, but the boundary is all A, and these lines are supposed to show the connections of this region to the rest of it. Right? If you had such a region, it's very easy to see that you can construct a zero energy wave function that lives entirely on the majority side. So there's any degrees of freedom, and does not live on any of the majority sites outside or the B sites outside. It only lives inside and only on the majority freedom. And you can convince yourself that there's NA degrees of freedom, and NB constraints such a wave function has to satisfy. And since NA is bigger than NB, you have exactly these many topologically protected zero modes in any such, right? Region by. And this is topologically protected because it's just an argument about constraints and variables. It doesn't depend on the Tij. If the Tijs take on some special values, you can get some extra zeros, but you can never wipe these out. And this is an example of some extra zero mode coming about because you have kept all the Tij equal. Right? It gets wiped out the minute you put some disorder. This one is an example of a region of this type. Okay? So that's all. That's as far as we could go in this old work, but it left a very key question unanswered. So these hand-drawn examples, which I used to sit and doodle on in the train, they just provide some lower bounds on this density of state. Delta function at zero energy, its amplitude you can bound below by drawing pictures, right? But if you just do the calculation with some multiplication arithmetic, try to find how many zero modes there are in the sample, you find the computed values much greater, orders of magnitude. And so what actually determines this density of zero modes was the big question at that time. And the first clue was, as I was saying, it's local sublattice imbalance that we are exploiting to construct. There's something else that happens when there's local sublattice. Something very familiar to a StatMech audience. And that comes about if you start thinking about dimer covers of it, or the problem of matching of the lattice, right? Every time you have a region like this, you see that actually such a region will also trap some monomers in any maximum matching. Because if you think about it, in any maximum matching, by which I mean you want to cover as many frequencies as possible with that without letting two dimers collide. In any maximum matching, if you had such a region in the lattice, all the B sites on the boundary would have to match inwards. And even after doing that, you would be left with these many more. Right? So that was the first clue that there is some way of thinking about it that's sort of very StatMech. And this was actually confirmed when we sort of looked up the literature. We found out that this idea we had been anticipated by at least 60, 70 years by Longwell-Higgins in a completely different context. And translated to our language, his result was that the number of monomers in any maximum matching of the graph is equal to number of topologically protected zero modes in the tight binding model of that. Yeah, this is the statement. And just in case there's somebody in the StatMech audience who's not heard about dimers and matching, here's a little language primer. So by dimers, we simply mean hard rods on the length of the lattice, which will constrain that two of them don't touch at a vertex. And in graph theory, this is called the matching problem, or in computer science. And the real question is, can a lattice with an even number of vertices be perfectly matched? That's the question in this kind of problem. Of course, if it's bipartite, you will at least need the total number of A sites to equal the total number of B sites. But even after you satisfy that global constraint, you may not be able to find a perfect where every vertex is covered by that one. In that case, you settle for a maximum matching that have the minimum number of unmatched vertices. So locations where the vertices are unmatched, you will say those are the locations of the monomers, and that will change from maximum matching to maximum matching. Because typically in a typical graph, there will be an entire entropy density worth of maximum matching. That's why there's an entropy density worth of perfect matching on, let's say, the square plane, right? So you will have monomers at some sites. Post the monomer depends on which maximum matching you look at, but their total number is always the same. So now we come to this question again, back to the original question. So after all this, where do these modes live, right? And so that now translates to a question we felt, which is how does one find a complete set of these archetypes? You have to be a little bit careful here because once you have a bunch of zero modes, all at exactly the same energy, there's no particular meaning to say where the modes live. Any linear combination of modes is also a zero. So you could have a wave function that lives here, a wave function that lives there, you take a linear combination, that's also right. So what we are really asking in linear algebra language is, does this idea we had allow us to get a useful sort of maximally localized basis for the topologically protected part of the zero mode? That's really what we're asking. So this we puzzled over for again quite a lot of time until some computer science and math colleagues at GIFR told us that there's this entire structure theory of graphs. So when we looked that out, we found that it has exactly what we need, and the particular version we need is this theorem of Dulmach and Anderson, the reference, and this relies on taking any maximum matching of the graph, can be any one, and so there are monomers in some particular locations. And then you build this sort of forest. You start with a monomer, go along any of the unmatched edges from that monomer, then follow it up with a matched edge, then an unmatched edge, matched edge, unmatched edge, like that. So that's an alternating path. So you go along alternating paths from one monomer, and you label all the vertices to each of the graph as even, odd, or unreachable. Even if you reach them with an even number of steps, or if you reach them after an odd number of steps, and unreachable if they are completely unreachable from the monomers via alternating paths in the particular maximum matching you start. You just do this labeling. And what these gentlemen say is that this labeling is unique. It's a property of the graph, not a property of the maximum. You can take any one maximum matching and get these labels E, O, and U, and you can take any other and you get the same labels for it. That's the theorem. The uniqueness is the theorem. And this we realized we could exploit in a very nice way to construct what we want. So if you now think about it, you can delete all the unreachable vertices and the connections. You just delete them for our purposes right now. The unreachable vertices, incidentally, are the vertices that are always perfectly matched in any maximum matching. And they break up into these connected components that I'm going to call p-type regions for later use. But right now, let me delete them. And I can then see that the rest of the graph decomposes into exactly the kinds of regions I've been talking about. They'll have a site boundary, which is locally in the minority, and in the bulk, the other sublattice will be, right? So this is the main content of the progress we made on the theoretical side. We realized that using these labels of Dulmach and Mendelssohn, and the fact that they're unique, we can very efficiently construct a complete sort of basis for these zero modes, these monomer characters, right? So that is the content. So now with that set up, let me switch gears. In everything I'm saying so far, the sort of elephant in the room is the fact that the lattice is not fine. But I'm using that very heavily. The whole thing relies on local sublatticing. But there are very natural problems of the type Sumati talked about, where people claim that you can come up with these devices or platforms or exotic states of matter where defects will carry in their core Majorana. And if these defects are very far away from each other, they won't mix and they'll be real Majorana mode. But in any other system, they're not infinitely far away and there's some weak mixing between. And if you want to ask about the weak mixing and its effects on these Majorana modes, you generically start with a quadratic form that looks like this. This is the quadratic form for what some people call a Majorana network. So it's just a quadratic form with Majorana creation operators eta r coupled by an anti-symmetric purely real matrix. So I times that is your Hermitian mixing amplitude. So now, if you diagonalize this and look for its actual eigenmodes, these are not Majorana modes typically because they're mixed, they're lifted away from zero. But you can again imagine that some zero modes survive the mixing. And in that case, you can use those zero modes to define collective Majorana degrees of freedom that are genuine Majorana fermions protected from this, that exist in spite of, right? So now the question becomes the question of sort of topologically protected zero modes of a purely imaginary anti-symmetric. And the basic picture in our mind then, in this case, was that odd cycles of the graph host trivially a zero mode because there's sort of symmetry E going to minus E and one eigenvector of such a motive isolated from everything else will be at zero. But of course, these motifs will not be isolated; they talk to each other. And so, if you now imagine having an odd number of these, if you imagine having these odd cycles coupled to each other via other sites, and if the number of motifs is more than the number of sites that they couple via, you can again make an argument and say you will get zero modes in any such region of the lattice, locally independent of what happens in the rest of it. This was the rough idea. And again, you want to try and systematize that. And you notice, again, the key observation that such motifs will also trap monomers of any maximum value. This is the key observation. For example, this region, just the rest of the graph is whatever it is, I don't care. In any maximum matching of the full graph, this region enclosed by dotted circles will host two modes. Must be the case because you can just make a local argument. So this was the key observation. And so then again, you're back to the same question. Is there some structure theory now of general graphs that I can use to classify such things? And again, we got lucky. First, we checked as a reality check that this gels with the theorem of Lovash to prove in this paper that even on a general graph, the monomer number in maximum matchings is equal to the number of topologically protected zero modes, this time of the anti-symmetric adjacency for general graph. So this, if you wish, what we just argued, provides us a local proof. This observation provides a local proof of this state. And then now to make this systematic, we have to go to the structure theory for general graphs that goes under the name of Galai and Edmonds theory. So in this Galai-Edmonds theory, it's very similar. You again classify things according to odd, even, and unreachable. And again, the labels are independent of which maximum matching you started with. But then the conclusion you can draw from it is that, again, there are these perfectly matched regions that are kind of separated from the rest. And now you have these odd cycles or odd cycles built inside odd cycles type regions, which talk to these other vertices. So this is the structure that you can prove from this Galai-Edmonds theorem on the uniqueness of the labels. This goes back to the seminal paper of Edmonds. And now this gives me this alternate proof I was talking about because I can construct sort of a fake bipartite graph. I can delete all these vertices and these connections. I can call all these guys B-type sites, let's say all the O's. I can delete the connections between them, keep only the connections between the O's and these odd cycle motifs, which are called blossoms. Those blossoms are actually inspired by this terminology. And then each such blossom would host one would-be mode, but they mix. And then in this fake bipartite graph, you make an R-type region, and again you count, and you know where to construct the zero mode. So this is the general idea. And the main point I want to get across, very good, is that this leads me to something very tractable, computationally tractable. I can, making one maximum matching of any graph is a polynomial time algorithm that is taught in like second year computer science classes. Take that code, you run it on your diluted graph, and you can then get these labels, EO and unreachable. From that, you can construct these R-type regions, and then you can just look at it, right? And you know exactly how many zero modes will live inside each. You don't know their wave functions because that depends now on the TI or the EI. But you know so many modes will live localized inside that region by region. Right? So this kind of motivates or opens the door for a detailed computational study of the random geometry of these R-type regions and their complements. These P-type regions that post perfect matchings in any maximum matching of the region. So this is sort of the first part of the talk, and I know I went a bit fast because I also want to show the results, but if there are any questions, I'd like to pause because This is kind of important.
Yeah,
Yeah.
right. So if you have a number of zero energy modes in the system, in the R-type region, they are not exactly localized at one point.
That's right. But
Then if
we
you
use the
say
statement,
one by one,
the statement we are
not
making
the-
is,
not the-
I can give you the region of the lattice, and I can tell you how many linearly independent null vectors there are. And then if you construct them, you have to of course solve the linear algebra problem, where you find some orthonormal basis of those modes. But I know how many live and in exactly which region. And so this I've done without doing any calculations that involves real numbers, purely by combination. That's the power.
and you can have actually exactly localized zero mode if you have an isolated side. And
Yeah, so that's the trivial case. The point we're making is that generalizes in a very natural way to these arrays.
So are you taking those into account? Those
Yeah, so those are trivial arrays. Single isolated site is a trivial array.
But if your single isolated side is inside that R region,
No, then it's a different array. There can be array regions inside array. Right? So it's not that straightforward. It is true that you get a complete and non-overlapping set of regions that gives you all the zero modes and all the places where monomers live with local information. How many live in each one? Right? And in fact, exactly the point you're making that there can be R-type regions inside R-type regions is what stumped us for, I don't know, like a year and a half when we were trying to do this by hand. Because we were overcome every time we do it. You know, we would construct some big region and say there are so many modes in it, and there'll be some smaller region inside which has some independence.
we are also stuck there. That these isolated regions. Why do we think of that physically? But physically,
I mean, they're there. I mean, you know, with what density they will occur, they will cause any problem in anything. They're sort of the trivial aspect of the problem. Yeah.
The A sides and the B sides,
Hmm.
they deep talk to each other. Like, through some 7 years.
You mean A and A?
A,
Yeah. Yeah.
A and A and
Yeah.
B.
Yeah. So let me go back.
Change your,
No, so that's actually before we did the non-bipartite thing. So the main motivation for this was exactly your question. What happens if I now add A? Because there's a natural way in which I think of the triangular lattice, the square lattice with one die. So the question was, I've done this on the diagonal square lattice. What will now happen if I just add a few of those bonds that make it a triangle? That's what we were starting with. And before I kind of realized all this, just thinking about this, there's one statement you can do. Right? You can realize immediately that if this number I is odd, right? Then when you add these AA couplings, you can prove actually one zero mode survives in every R-type region that has an odd imbalance, and none survive if there's an even. That much we know, right? So that's a perturbative. So now this is now here real numbers enter the picture to test that. This is a perturbative statement to first order in perturbation. So you have all these zero modes, you want to know whether they're lifting or not because of your perturbation. And the statement is they will all lift if IV is even and if IV is odd, one will survive. To first order is perturbation. But beyond that, we couldn't see anything. And so that was another large period of frustration where we were stuck until we realized that the right way to think is this. Okay. Okay. So any other questions about the setup? Okay. Good. So now I'm doing numerical experiment. But I've not done anything. The students have done numerical experiment. So let me show you the results. So we look at site diluted, triangular, and Shastri-Sutherland lattices to look at non-bipartite group. Square and honeycomb to look at bipartite. And in 3 dimensions, we looked at the cubic, which is bipartite, stacked triangular and corner sharing octahedral, which are not. So we try to do whatever we can with whatever resources we have. And we just do the most straightforward thing in most cases, just uncorrelated site dilution. Right? So the disorder is completely uncorrelated. But when we are looking at the bipartite lattice, to avoid sort of triviality, we impose a global compensation principle. After we've diluted the lattice, the number of A sites will always equal the number of B sites global. Right? Otherwise, there'll be some trivial extra zero modes, which we don't want to worry about. They'll contaminate what we're doing. And we characterize this random geometry in a bunch of ways. We count the number of R-type regions, number of P-type regions, and divide by the volume. We count the total number of sites in an R-type region or a P-type region and divide by the volume. So these are densities. And we count the total number of zero modes, or total number of monomers and divide by the volume. So this is the monomer density. And then we look at things that relate to the large scale structure, which
The dilution is above partnership threshold.
always be. So the pure, so when I dilute the lattice, if you just look at the geometry of the lattice, there's one large connected component that contains essentially all the same. Right? You're well below the population transition, the geometric population. But there is a different kind of population phenomenon, and to see that, we look at the largest R-type region and its mass density, largest P-type region and its mass density, the probability that a single region spans or crosses or wraps on a tool. Okay. So we just monitor all. So let me tell you what happens in the bipartite case. This part is published. So first, the number density of R-type regions, honeycomb at square, goes down quite quickly as you reduce the dimension. This is not surprising, and this is a thermodynamic quantity. No funny business. It converges to the thermodynamic unit. This is linear size by the way. But R-type regions take over the lattice. The number is going to zero. Number density is going to zero, but they take over the lattice because the fraction of sites contained in R-type regions grows to 1. The picture then is that these regions are getting very big and there are few. Right? So now you start thinking of the population. And here's a picture that should encourage you to think of population. This is the largest 3 R-type regions, RA and RB. And a honeycomb lattice at 5% dilution, uncorrelated side. So you've done nothing with your actual dilution to encourage any large-scale correlated structures, no problem. But if you look at these monomer carrying regions, these R-type regions, the largest 3 look like this. This is the largest, second largest, third largest. And in this finite sample, at least the largest look like it spans both sides of the wraps around twice, right, in 2 directions. So then we start being more quantitative. So is there a population transition associated with R-type? So we look at the probability that a single region can be used to walk from one end to the other. We're doing it on a torus, so we're actually talking about wrapping. It's the same thing. And if there was a population transition, these curves, which correspond to different sizes, would have crossed. But they don't cross. They appear to want to cross, but they never seem to cross at the lowest dilutions we can go with. But it looks like there's some scaling there. So we tried an ansatz where we said there is incipient population. There's a population transition at 0 dilution. So when we do that, this is beautiful scaling we get with an unusually large correlation like this. But we have a fairly large range of sizes. These are big numbers, and we get good scaling, and it's universal. So there's no reason for it to be, but so we claim there's a universal incipient population phenomenon associated with R-type regions getting very large in 2-dimensional site diluted. In 3 dimensions, there's actually a population transition when we look at the same thing because the curves cross, and then we can scale it. Right? Like in regular population, we get a value of nu. Interestingly, this value of nu is very similar to 3D geometric population. But the physics is different because after you populate it, there are 2 infinite clusters, not 1. There's one RA region that's spanning the whole lattice and one RB region. But if you lower the dilution further, there's a second phase transition, which is a spontaneous sublattice symmetry transition, where spontaneously A or B, one of them wins, the other stops spanning the lattice. This one grows at the expense of it. So that the order parameter for that is the mass in the largest A-type region minus the mass in the largest B-type region, modulus divided by the total mass. And that jumps. So there's a first order transition, which is a sublattice symmetry transition deep inside the population. 4 minutes. So now let me switch to the non-bipartite case. Part of this is on the archive, but not yet published. We ran into a little hiccup here. It got moderated for 3 weeks. Something about our paper was suspicious here. And then another one is being written. So now I'm looking at triangular and Shastri solution. Again, this is the site dilution. And again, the density, this time I'm showing the density of 0 modes. It comes down smoothly to 0, no features that you can see. It's not really 0, by the way. If you put it on a log scale, it's just going continuously. But now here's the interesting difference. If you look at the fraction of sites in R-type region, what I was calling M to R here, right? It doesn't seem to grow to 1. But it seems to start getting very noisy. And we haven't done sort of bad numerics here. In fact, we have done more averaging, more samples, more care has been exercised in this region compared to that. But no matter what we do, it's not. So when we looked in detail, we realized it's because there's something intrinsic happening. there's a bimodality in the large scale delay. So some half of the samples roughly have very large number of sites that live in R type. This ratio is at this side. The other half are very small. So the total density of R type regions is fine below a certain threshold. So we were wondering what this means. We looked at the fraction of sites in P type regions. Same thing, it's binary. So unlike in the bipartite case, both R type and P type regions can become very large. But which one grows seems to depend from sample to sample. Or they're all nominally identical samples, right? And they're anti-correlated. So if you now decompose the samples into R type or P type based on which is the biggest region, you find that the other kind of scales to zero, right? And so this is what I'm showing here. So conclusion then is that there's this dramatic violation of self-averaging in the thermodynamics, which I'm showing pictorially. So the color coding is consistent across the two pictures. Blue and brown represent the largest and second largest R-type region, and purple and green the largest and second largest P-type. So here's a typical sample, which is I would call R-type. The biggest region is R-type, which is spanning the largest. This one is P-type. So this thing which is tiny here is grown, and the others are small. So you make a million identical samples, nominally identical. Some of them will have huge R-type regions that span the lattice. Some will have P-type regions. This is a very dramatic violation of self-averaging. Should be reminiscent of these multi-value pictures for swing classes. Right? And there is a genuine percolation transition below which this happens. So I'm just showing the scaling plot for the crossing problem. We get good scaling exponents, which are now inconsistent with 2D percolation, which is 4/3. And we can sort of look at the eta by looking at the mass in the largest cluster. So it looks like a percolation transition, but below the percolation threshold, self-averaging is violated. Right? And let me just stop by showing you the 3D phase diagram and inviting questions on it. Because we've done a lot of work. This is almost baroque, the phase diagram, but I don't have time to talk. But let me also flash. No. Thank you.
So if there are no questions, then let's can just
It works.
So the next talk is by Krishnendra Sengupta, and he is going to talk about aspects of Hilbert-Swiss fragmentation.
Hello. Hello. Okay. Good morning, everybody, and thanks for inviting me here. Great conference, and so the title of the talk has changed a little bit. It will be around driving state normalization hypothesis violation in different quantum systems. And first, let me acknowledge my collaborators. Bhaskar, who is now a postdoc at University College London, Amesha, who is here, and Arnav, who is my colleague at IIT Kolkata. So the first set of work I'm going to talk about done by them. And the second is in collaboration with Shomshuto, who is, I think, in the audience, with a student at IITS this week, and in learning with a friend and collaborator from Paris. And these are some of the publications if you want to check. So let me first talk about what this isostate normalization hypothesis is. So to understand this, it's useful to consider a generic quantum system, and I can take wave function and expand it in the basis is the eigenvector of the system. Now, if I try to think how the transformation of a generic operator for this state progresses, I will see that two lines of algebra is with this particular expression. So there is a diagonal component and the off-diagonal one. And then if I try to look at the long-time behavior of this, there are a few issues. First one is that it seems that at long time when I can do this part, just average, which averages out, the steady state value of O seems to depend on the overlap coefficient, which means that the system retains memory of the initial state. It never happens in an algorithm. So that's the problem. And the second one is that you could ask that how long does it take to reach the steady state? And the answer is when this time is large compared to this energy gap. And that is really a very long time because in the middle of the Hilbert phase, the gap between energy states is exponentially small in system size. So the system takes an incredibly long time. And this is in contrast to what we actually see in it. We don't take that much time to reach a steady state. So it turns out that invoking some structure for this matrix elements of operators essentially remedies the problem. One possibility is to invoke random matrix theory and just say that, well, my diagonal element is just a constant and the off-diagonal element is 0. That's the random matrix theory prediction for arbitrary matrix element. And this, of course, tells you that both of these problems go away. However, it provides an energy independent answer for the steady state, which is not what we see. So to remedy this problem, there is this hypothesis called the eigenstate normalization hypothesis, which tells you that this matrix element has a special structure, and this holds only for quote-unquote typical operators, which are reasonably local. And the structure is something like this. Okay, so here this O and F are smooth function of their arguments. Okay, omega is the energy difference between the states M and N. E bar is the average energy. And therefore, if you just take this, and S is the entropy, and therefore the off-diagonal elements are exponentially suppressed because this entropy is very large for a thermodynamic system. And so essentially, if you calculate the steady state value by doing this, the long time average, you find that it goes to trace of the diagonal ensemble. The diagonal ensemble is the point where you retain only the diagonal components of the density matrix. And this result coincides with the thermodynamic result, which is the result obtained from this microcanonical ensemble. And this fact relies on the energy fluctuation of a many-ordered system being sub-extensive, so that you can expand the further values around some average energy, and the rest of the thing would be public. Okay, so this essentially tells you that if you look at the time evolution of a given operator, at long enough time you go to a steady state, which has a fixed energy density and therefore a fixed temperature, and this essentially is the thermal. If you apply this to a driven system, it just goes to an ensemble where this effective temperature is infinite. So that's the infinite temperature. So the prediction of this ETH is that it will always be a thermal steady state, but this relies on ergodicity, and therefore there are cases where this doesn't work. One of them is of course integrable models, because of presence of a large number of convex quantity will violate this ergodicity and therefore violate ETH. The second one is many-body localization, provided it exists. The system will become non-ergodic due to very strong disorder. I'm not going to talk about these two. What I'm going to talk about is a more subtle aspect of violation of ETH, which can occur due to a special class of eigenstates in the Hilbert space. And this leads to long-time coherent oscillations in the expectation value of this operator rather than a steady state value. And also due to fragmentation of Hilbert space, which can occur in constant system, which leads to loss of ergodicity. Which leads to lots of ergodicity, and this phenomenon is known as problem fragmentation. And I'm going to show you realization of both of this in context of driven systems. The experimental motivation of this comes from a series of Rydberg atoms, where which has van der Waals interactions between two atoms in their excited states. And this experiment has been done in 2017, and it has become a standard experiment in the field. where you couple this Rydberg excitation, the Rydberg atoms in their ground state and excited state via some external lasers, and the effective low energy Hamiltonian consists of coupling between the ground and the excited state, density, and this detuning, which is the difference between the externally applied laser and the energies of these two states, atomic states, which acts as a chemical potential, effective chemical potential for exciting this Rydberg excitation, and this van der Waals interaction between two Rydberg excitations. So if you make this van der Waals excitation, which is a tunable parameter, strong enough, what happens is that you essentially do not allow Rydberg excitations to occur at neighboring sites or maybe next to neighboring sites. This phenomenon is known as Rydberg blockade. And in the experiment, using this Rydberg blockade, people have gone to states where there is Rydberg excitation in every second site or every third site. But the thing that I wanted to discuss here is that starting from a state like this, if I may suddenly quench my detuning parameter and come to a regime where this detuning is 0, so that I am left with only this term, then and I measure the domain wide density, which is like probability of having two Rydberg atoms in their ground state side by side. That's the effect in this otherwise equivalent state. It turns out that they show an oscillatory behavior rather than a quick thermalization. Interestingly, if I start from a Rydberg vacuum state, with all atoms in their ground state, and do the same experiment, it's going to have thermalization very quickly. And this, of course, resulted in some theoretical questions as to why these are happening, and these were attributed to a special class of eigenstates known as the quantum stars, which was done by Amelin and many others subsequently. But what I'm going to talk about today is the fate of this quantum stars, provided you take this system and drive them theoretically as a function. So that's the idea. So we call them Fluke quantum stars because these are systems described by a Fluke Hamiltonian. But before going into this, let me just set up the model. So the effective model for this Rydberg excitation is something like this, where this is the detuning parameter delta, and this is the Rydberg excitation. So since there are two states per site, I can go into a natural scheme of representation. And also, I'm going to talk in the regime where this neighboring states have a very large Rydberg blockade between the two Rydberg blockade, so that two Rydberg excitations will never appear neighboring sites. So this is in this limit, this constraint that two Rydberg atoms are never going to occur in two neighboring sites can be implemented by a projection operator given by this, which just tells you that you can, so you take this Hamiltonian and you get into this regime. It turns out that the modification that you need to do is that you can flip a spin only if this projection operator on the neighboring sites ensures that the spin on the neighboring sites are down. So that's basically the effective spin model. And if you put this lambda equal to 0, that is, if you take this detuning to 0, this is the Poisson experiment. So in what follows, what we are going to do is that we are going to start from this Rydberg Hamiltonian and study a simple square pulse protocol where I drive this effective magnetic field or this detuning term according to a square pulse protocol given by this. So this lambda t just changes sign between the two half cycles. How do I treat this system? There are two ways. One of them is numerical and exact, using on finite size system using exact diagonalization. And for that, what we note is that this is for this protocol, the evolution operator which controls all the dynamics of the system essentially can be written in terms of product of two exponentials. And these are known once you know the eigenstates and eigenfunctions, which are known numerically through exact diagonalization of h of lambda and h of minus. And once you find this, it's easy to find the evolution of any operator. And in particular, we are going to look at the density correlation out here. And this is the operator, this is the expectation that we are able to make. This U is also related to the Fluke Hamiltonian and the eigenstate that we obtain are also eigenstate. However, this analytical calculation can be backed up by some perturbation theory, and particularly when this drive amplitude is large. In that case, one can basically this. Okay, so here I'm going to be in the regime where this drive amplitude is large, and in the regime where the drive frequency is either high or intermediate, but not too low. It means that, okay, in this regime, what we can do is that at the 0th order, because the drive amplitude is large, I can calculate a U0, which only contains the drive term. And then the effect of the other term, which is the, which basically is this W, can be taken into account perturbatively. And this perturbative Fluke Hamiltonian can be exactly calculated. It's a few lines of calculation. But the interesting part is that this first order Fluke Hamiltonian is exactly like the PXP term, except that now its amplitude is modified by this factor sine gamma by gamma. And therefore, there are special frequencies where this gamma goes to 0. Gamma goes to an integer multiple of pi, where this first order Fluke Hamiltonian is that. Now, we already know that this quantum scars exist in the Hamiltonian of this PXP model from Avanin-Allar's work. So, if your major term of your Fluke Hamiltonian has this quantum scars, you expect this oscillatory behavior, provided you start from a rectus symmetric state. However, this tells you that there are special frequencies where that behavior is just going to go away. And this would be a non-monotonic dependent because of the presence of this cycle. So we check for this numerically, and this is exactly what we see. So for example, when my frequency is very large, we reproduce this result by Avanin because that's sort of the Quench limit. And this is oscillatory dependence of this correlation function. However, at very small frequency where none of this perturbation works and the first order Fluke Hamiltonian doesn't have any meaning, you see that there is very rapid thermalization. In between, there are frequencies at which you see signatures of this thermalization and other frequencies at which you see this oscillatory behavior. And this behavior is clearly non-monotonic because you see that this omega d is small compared to this the other. Also, if we look at the half-chain entanglement entropy of this Fluke eigenstate, that is, if you take an eigenstate, construct a density matrix, integrate out half the system, and then look at the entanglement of this, one finds that at this high drive frequency, there is a band of states which are outlier here, which has low entanglement, and these are the scars, and one can check that the entanglement of this goes roughly as log L, whereas the other thing here is in the thermal band, where the entropy goes as a result into a volume law, linear enough. So this shows the presence of this quantum scars out here. However, if you go to small frequencies, you see that everything is in the thermal band, scars disappear, which is consistent with what we see here. And then there are other frequencies at which the scars either exist out here, a small amount of them, and here they don't. So
for omega 1.3,
these are isolated states that is written outside, but these do not. So these red dots are the ones which have large overlap with the initial state and they contribute to the dynamics. These states do not contribute to the dynamics. So even if there are scars, they are not going to contribute to the dynamics provided we start from this initial state. So now let us look at the behavior close to a special frequency. So close to a special frequency, what happens is that you have this oscillatory behavior when you are slightly added. As you approach this special frequency, which is the 7.75 in this set of units, it turns out that these oscillations go away and you see very rapid thermalization. But when you lower this frequency further, you see that this oscillation persists. And the scar structure is a bit messy here, but one can see that, at least at 7.75, everything is in the thermal band. Here, there are a couple of scars which has large overlap and they lead to these oscillations and so on. So you see a transition between behavior which is oscillatory to a behavior which is VTH, rapid thermalization. And we see several such transitions between within a range of this parameter lambda over omega d. At lower frequencies, these thermal regions will take over. And I can show you a small phase diagram out here in the lambda omega d plane. So I am here in the large lambda limit, so that the drive amplitude is large. So in the high frequency limit, you see that these are the regions where the thermal behavior is there. These are the special frequencies at which the first order PK Hamiltonian disappears, and you lose the scar-induced behavior. However, as you go lower in frequency, these regions become more and more dense, and at low frequency, they completely take over the thermal range. But there is this possibility of tuning coherence in different mini-Gaudic systems by a drive frequency, where you can see this. So what we also found, and I'm going to be quick about this, what we also found here is that in these driven systems, we of course have scars which are large overlap with Z2, but you can say that these are sort of analytic continuation of scars which are in equilibrium. But there are special type of scars which have no equilibrium counterpart. These are actually the Fluke scars, because there are these states which leads to this oscillatory behavior. But now when we start from the Rydberg vacuum state, these are overlap with the zero Rydberg sector. So if we look at the diagonal ensemble value of this operator in J plus 2, which we call it 422, and we plot it as a function of frequency, starting now from the ground state, we find that at high frequency, this is going to go to whatever the ETH predicts, which is this blue dotted line. However, when you go to lower frequency, it turns out that the behavior changes drastically. So there is this region where this behavior is larger than the thermal value, which we call the superthermal region. Okay, and here, if I show you the time dependence of this, you are going to this operator, you are going to see these oscillations. Then there are these special frequencies around 8 and 4, where the system completely freezes. Okay, for times that you can monitor, the system simply remains in the ground state and never moves. And this happens at frequencies delta naught over 2m for integer s. And this is dynamical freezing. Driving the system at a particular frequency simply doesn't allow a matrix element which connects to any other state from this Rydberg vacuum. And then there are these regions where the steady state value of this operator is half thermal, which is something you usually do. So I'm not going to describe this in detail, I'm going to refer to the work, but where the reason for all of this is given. But now let me show you the time dependence of this. So essentially, I plot it as a number of drive cycles. So if I'm at high frequency, you see this rapid thermalization, which is what is expected, because now I'm starting with the Rydberg vacuum, and therefore the traditional scars really do not continue. However, in this region where I have this subthermal stuff out here, you see this oscillations come back. And when you look at it, we find that these oscillations are due to scars in the superthermal regions, which has very little overlap with Z2 state, but have a finite overlap with zero state. These are the ones given in red. So these are the scars. And they coexist with this green dot, which are the scars which have overlap with the Z. So the same system can have different atypical non-thermal states, which have overlap with different initial states. And therefore, these only occur when you drive the system, and they have no counterpart in the equilibrium process. So there is also this dynamical freezing in which you see that the system simply doesn't move, and this subthermal region where the system attains a steady state very quickly without oscillation, but that steady state is below the ETH predicted value.
These are for different frequencies.
These are for different frequencies. So, for example, I have chosen this to be the frequency for dynamic physics, and somewhere here to be the frequency for the subprimal region, somewhere here to be the frequency for the superprimal region, and way out here for the health. Okay. So okay, to wrap this up, so what I wanted to say is that the driven system can have scars which are of different variety, and there are typical two-phase scars which do not have a equilibrium curve. Now, let me move on, and in the remaining 8 minutes that I have, let me very briefly talk about a fluke realization of this strong Hilbert fragmentation. So, Hilbert space fragmentation typically is a phenomenon which constitutes breakdown of Hilbert space into an exponentially large number of dynamically disconnected sections, and this typically happens because of some constant in the Hamiltonian. Now, the fragmentation is usually observed in the computational basis. It doesn't make sense to talk about fragmentation in the eigenbasis. Everything is fragmented there. But the classical Fock states as the number basis, is one such computational basis. Now, such a separation of Hilbert space into dynamically disconnected sector also happens because of symmetry. But the difference here is that the number of fragments, at least for strong Hilbert space fragmented, is exponential in system size. Okay, whereas for symmetry it's never that. So that's the difference. Yeah.
So that digital length will also be a smaller exponential, or
It will be a smaller. Yeah. And still the ratio is exponential.
And what is
Okay, so the weak fragmentation is when this goes to 1. Essentially, the largest sector just finds the entire Hilbert. The ratio goes to 1. Scars is an example of a weak fragmentation because the thermal states just form the exponential.
But there are still something.
There are still some. Yeah. So most of the models exhibiting the strong Hilbert space fragmentation are 1D, but there are some 2D models and one which all of them need a lot of work. Now, what are the signatures of this strong Hilbert space fragmentation? One is memory retainment. So you start from a fragment, you don't go out of this fragment during the dynamics. So the system retains some memory of its initial state. And the second one is that the deviation of the entanglement entropy from its symmetry or painful. So if you take a thermal system and you look at the entanglement entropy at large times when you drive it, it goes to a page value which is roughly like the log of the dimension of the Hilbert. This is different. I'm going to show this for this kind of Hilbert fragment. So one example of such a model is this particular thing, which is worked out in this this paper. So it's a fermionic model with correlated hopping, and this projection operator just ensures that the hopping doesn't change the number of bonds with particles on both ends. Okay, and this can be thought about as an effective model with the large V limit of a fermion chain, where V is the nearby interaction. And this, the concept quantities in this model is the fermionic charge and the number of bonds. And you see that, with this constraint, this projection, a state like this, nothing can ever form because, take this particle, for example, its nx plus 2 is 0 and its nx minus 1 is 1. So this thing just goes to 0. Okay, so this Hamiltonian just vanishes and it doesn't. But there are other sectors. Okay, so there are many such sectors, and there are exponentially large number of such closing states. And so what we wanted to do is to see whether this phenomenon can occur in a given system. And what we found is a pre-thermal, and what we found is that the answer is yes, and there can be a large pre-thermal regime before the system ultimately attains a thermalization. One can see signatures of this Hilbert space fragmentation. So for this, let's consider a chain of spinless fermion with nearest neighbor hopping and density-density interaction. And we are going to sort of take a drive protocol, which could be either a square pulse or a cosine protocol, and we are going to drive the interaction now. That's the protocol here. So in the high drive amplitude regime, one can just do this Fluke perturbation theory, which I showed before. And it turns out that, the Hamiltonian has a hopping term now, the Fluke Hamiltonian. First order Fluke Hamiltonian has a hopping term, which is something like this. And this familiar projection of nj plus 2 minus nj minus 1 just appears in this Hamiltonian. And this can be worked out in a few lines. And this gamma naught essentially is a dimensionless drive frequency. It's a ratio between the amplitude of the drive and the frequency. And it turns out that if this f gamma naught goes to 0, this Hamiltonian reduces to the old Hamiltonian out here. Which means that the first order Fluke Hamiltonian is going to give you signatures of Hilbert fragmentation at this special drive frequency. However, there is still this question that there are higher order terms. They are not going to obey this kind of projection, and they can destroy Hilbert's fragmentation. And the expectation was that for large drive amplitude, this kind of higher terms are small, and you can have a large pre-thermal region where the signatures of this Hilbert's fragmentation going to occur. And that's exactly what we see. So since I'm running out of time, let me just quickly go through the entanglement entropy. And so what we do is that we start from an arbitrary state in the Fock space, so arbitrary Fock state in the Hilbert space, and we drive this. Okay. So when we drive this at a frequency which is other than the special frequency, and for drive amplitudes which are reasonably large, within a few tens and hundreds of cycles, it just goes, the entropy grows and it goes to its phase value. But the phase value is roughly log of the system size minus half. It's not quite so, it's a bit more complicated because the symmetry is of the center, but that's a different thing. But if you do the same driving in the regime where you are using the special drive frequency as your drive frequency, it turns out that as you increase this drive amplitude, your entanglement entropy doesn't really goes to this. It doesn't really goes to this page value. It goes to the page value of the fragment from which this thing is drawn. And here we draw the state from the largest fragment, which is roughly whose entanglement is roughly 0.8 times the entanglement of this. And then what we also do is that we now keep picking the states randomly from the Hilbert space, and then we try to see what are the long time value of this entanglement entropy. And it seems that we find that for different initial states, the entanglement entropy saturates to different values of S. And this is a signature that your Hilbert space is fragmented into different pockets. So, okay. So one can also show that this autocorrelation retains its memory. I'm not going to get into the details of that. But here is a phase diagram where we show that this is the region where this Hilbert space fragmentation pictures are going to be seen, because this is where this autocorrelation of the finite value. And one can also study how the system behaves when you start from a frozen state. There is some very interesting oscillation. We can talk about this after the talk if you are interested. So to conclude, what we find is that this given system shows Fluke curve as well as a pre-thermal signature of strong Hilbert space fragmentation. These are typically phenomena which occurs in standard equilibrium or quasi-equilibrium quantum systems. However, here we have provided some examples that they occur in different periodically. So I will stop here and thank you for your attention.
There's this Outgalia Montronic commutant algebra way of thinking about things that are also taken across the flow basis. Does your example fit into that?
No, because they are going to fit in if you are just considering HF1, which is this Hilbert space fragmented stuff.
But not the flow case star?
No, the first term. And if you're thinking of expanding, first term is going to obey them.
I see.
But the second and the third and the fourth and the other term, they are all going to violate this.
And you need all those to.
No, so the point is that the question is, when does this violation show up in your any operator that you measure? And the answer to this is that after a long pre-thermal regime. And so, and that pre-thermal regime is exponential with the dry band. And that one can focus. So the idea is that within a very large pre-thermal regime, only the first order term is dominant. Those commutant algebra and everything is going to be approximately valid here.
That formalism works for that part.
Yes, but of course it's difficult. I mean, that is done for the equilibrium.
Yeah.
AC. And since this first order Fluke Hamiltonian is roughly the same as that,
So it works there. Right. Okay. Thank you.
In the interest of time, let us move on and let's thank the speaker again. So the next talk is a 15-minute talk by Shami Ghosh, and she's going to talk about eigenvector correlations across localization, transition, and normalization systems.
Hello everyone. First of all, I would like to thank the organizers for giving me this opportunity to present my work here. So this is a recently published work done with Professor Manas in at ICS. So I'll be talking about eigenvector correlations in terms of localization in organization systems. So to first start with, let's talk about localization. So we know that if we have field system in presence of all eigenstates are log-based, which are extended to the magnet, which are extended to the magnet. Now, and here the transport is statistic, that in case of in presence of imperfections, they can act as catalyst centers, which will actually diffuse the transport. Now, Anderson showed that in presence of strong disorders, the transport can cease and all of these eigenstates can become exponentially localized. And later shows that even in presence of short-range interaction, this kind of localization survives, which was termed many-body localization. So this localization is slightly different from Anderson localization in the sense that this is not exponentially localized, but they have very interesting properties like area content as well and so on. And obviously, memory of initial conditions as well. But all these are force systems, and one would typically expect that there should be some coupling with environments, and so hence the question was asked that what is the rate of localization when there is interaction with environment. And one way of addressing that issue is taking connecting a bar to the system and taking the system as bar in the whole system to study, but then there is a restriction in numerical simulations that the size of the system and both parts get extremely restricted, which makes it slightly difficult. Another way would be to think of some effective non-Cartesian Hamiltonian, where there is some gain and loss in the system due to some effective coupling with a bar. So we are not we will be considering this kind of Hamiltonians where we are not actually considering the exact details of the parts, where it is just gain and loss terms, which gives some non-harmonious in the Hamiltonian. So before going to the non-harmonious, I'll just briefly discuss how we easily identify localized states from localized states. So one simple way to see is how the wave function is spread over the given lattice, and if those if this is specially localized, then just by looking at the spread of this wave function, one can understand differentiate between the localized and localized states. And there is also another way of locating these localized states is through the eigenvalues, because specially localized states, because of absence of resonance have arbitrarily random eigenvalues. So if the eigenvalues are uncorrelated, we sometimes get, if the eigenstates are localized, then we get uncorrelated eigenvalues. On the other hand, extended states would give correlated eigenvalues. So by starting the short range or long range correlation between eigenvalues, one can identify this localization transition. Now, so these are this happens to be true even in non-Hermitian systems. So we have a previous work where we have studied disordered logic impacting non-Hermitian systems, where we have studied these correlation of these eigenvalues to identify a localization transition. But here we will be discussing about statistics of eigenstates. So, as I have said earlier, that one can look at how these wave functions are spread over the finite lattice. So one way, one quantity that quantifies that spread is the inverse participation ratio, which is the moments of the amplitude, wave function amplitude at the chosen basis states I. And from the scaling of this quantity, one can actually identify delocalized, localized, even multi-factor states. But in non-Hermitian systems, we have left and right eigenvectors which satisfy these bi-orthogonal conditions, which is slightly less restricted than the orthonormality in Hermitian quantum mechanics. So, so basically, what we have are left and right eigenvectors, and so one can define these IPs in terms of either right or left eigenvectors, and so it turns out that both of them has to be treated on equal footing because of the bi-orthogonality condition. These different left eigenvectors corresponding to different eigenvalues are not actually orthogonal. So this L alpha L beta can be non-zero even when this alpha and beta are indices of two separate eigenvalues. Oh, and actually forgot to mention that non-Hermitian Lewis will have complex eigenvalues in general. So these alpha and beta are indices of these two different eigenvalues. So here we would actually study the statistics of this quantity, which is the correlation between left and right eigenvectors corresponding to different eigenvalues, Z alpha and Z beta. So to quantify it further, we define this quantity where we resolve this O alpha beta in terms of the eigenvalue spacing. So this omega is now a complex number, which is the complex spacing in the spectrum, so this is a, I mean, if we want to study the statistics, this is the 2D data. Now, to simplify it further, we for this work we have considered this correlation as a function of just mod omega, where we are integrating out the azimuthal angle of this omega, and so this quantity has been studied in case of random non-Hermitian random matrices where there are some analytical results. So the definition of this non-Hermitian random matrix would be so I have a matrix where these RMN are different elements of the matrix which have both real and imaginary parts, and all of these are chosen randomly from a normal distribution. So for this kind of random matrices, if one plots this O omega as a function of mod omega, so there seems to be a power law divergence as a function of omega, and so which means that when I have two eigenfunctions which are very nearby, they are highly correlated. Their eigenfunctions are highly correlated, but farther eigenvalues are less correlated. And this omega to the power minus 3, this power law is, I mean, there is an analytical derivation for this power, and so just to so this for Hermitian matrices, this quantity is not invalid because of the orthonormality, this O alpha beta is delta alpha beta, and since we are considering this orthogonal correlation for different eigenvalues, so this orthogonal correlation is treated with 0. So what we wanted to study was, because we know what the analytical form is in the non-Hermitian random access unit. So what we wanted to study is how this correlation behaves as one goes across the localization condition, and whether this captures the localization condition. So for that, we have used this simple power law random eigenmatrix model, which is a non-Hermitian model. So it is defined this way that I have diagonal terms and off-diagonal terms both, which both of them has real and imaginary parts, and and all of them are chosen from uniform distribution, but the width of this distribution for the diagonal parts are 2W, and for the width for the off-diagonal parts decay as a power law as a function of m minus n. And I'm going to find out that the non-Hermitian accident parameter in this model is this imaginary part of epsilon n, because although these JMNs are complex, but because of this condition, if we didn't have this would actually go to the Hermitian power of anti-parametric model. So this model has been studied using this vector correlation and inverse participation ratio to understand if there is a localization transition. And this is the Venn diagram of that. So basically choosing the strength of the disorder and the power of the this power law decay of the off-diagonal elements, one can have a localized to delocalized transition. So what we are doing here, we are what is alpha? Oh, actually, alpha is P. So it is taken from another paper. So they have used the variable alpha for this. So what we are doing here, we are fixing the W at some value and varying the P to go across the localization transition and calculating this ion state correlation. So here is the plot that where so these darker colors are for smaller P when I'm in the delocalized phase. So there the power this divergent power is -3, and as one tunes this P, this correlation gets suppressed, and so we did finite size analysis of this, where I have calculated the power law this power for different system sizes, and we seem to see a clear crossing where in the delocalized phase for small p this power is supposed to go to 3, and in the localized phase this goes to 0. So we understand this 3 part from non-Hermitian RND, but to understand why this thing becomes flat, so we did some perturbative calculation when we are taking the limit of very strong W. In that limit, this off-diagonal elements now are just perturbations, and we can write the both right and left eigenvectors in this perturbative expansion, and which gives us some expression for O alpha beta, and we can plug in this O of omega function to get some estimate. So we seem to have very similar behavior as compared to our exact calculations, but then there are some regimes where resonance is offered for very small omegas. So since this is the first order perturbation field expansion, so for very small omega this is to hold, but then again we actually take into account of those small number of resonances by introducing this theta function, and which gives us a complete perfect match with this. So this is my summary. So we summarize that this eigenstate correlation is distinctly different in delocalized and localized phase, and in the delocalized phase is corresponds to non-Hermitian RMG. In localized phase there is suppression of correlation, and this power law with which this correlation diverges, that changes across the localization transition, and the system size scaling of that can capture the localization transition. And these are just some pretty pictures. So this is in the complex plane. So I was talking about in the mod omega function, but this is in the complex plane how this looks like, and there is some asymmetry. So we seem to catch this asymmetry also from just the first order probability expansion. And thank you very much.
It looks like bigger equivalent thing is that the size versus this.
Which one?
This T versus, I mean, for different sizes, yeah. It crosses at all the terms cross at single point.
Yeah, it actually is a transition. So,
Looks like beta equivalent.
yeah, I mean, it won't calculate spindle to study. It is relevant in some transition. It will for different systems that will be crossed. So it basically says that if I just increase the system size, then this can happen that this would just be a state kind of function where for t below this 0.7, I will have 3, and after that I will just have 0.
So, yeah. So this, it seems like the overlap of left eigenvectors, how it correlated with right eigenvector, that decides whether you are in a local expert or in a local expert. What, how would you explain that? I mean,
No, actually, it's not exactly the correlation of left and right. So
it's not left and right. Yes, overlap of left and right, that decides the.
Yeah.
How
So,
how to understand it? Other why?
yeah, so I have feel that I mean, when I have local X space, so these right eigenvectors are spread over some sides of the basis states of choice, and left are also doing the same thing. But when I have all the states are localized, and two eigenstates would have very less and less overlap, right? And that would be
So
true
this
for
automatically
both left
both of them.
and right both. So this
The product
quantity
is
captures
equal.
the together, captures together instead of. Any questions?
If not, let's send this detail. The next talk is by Dev, and he's going to talk about wave-bound liquid crystals in two dimensions.
Okay, am I audible? Good morning to all, and thanks to the organizers that I got this opportunity to present my work. So first, just one thing. Can you all just imagine these are just numbers and forget about them? Okay, because I have a lot of things to show, but because of that number, maybe I will just stop at some point in this presentation. So what we are talking about is the liquid crystals in 2 dimensions. So because we do theoretical studies, especially the computational physics, so we need a model. The model to represent the liquid crystal is called wave-bound liquid crystals. So that means this wave-bound potential, the interaction between 2 liquid crystalline particles, is a modification of normal Lennard-Jones potential. I'll come to that later on. So liquid crystals have one interesting property is that they have the orientational order. So normally, so far the 2 dimension, what I'm interested in is in its melting behavior. So in 3 dimension, the melting is going from, let's say, solid to liquid phase is a first order transition. But what happens in 2 dimension is it doesn't go directly from a solid to a liquid state, but rather there is an intermediate phase. And that phase is called hexatic phase. And it's proven long back that these transitions from liquid to solid, from let's say solid to liquid, through 2 different transitions with the in between hexatic phase, both of them are continuous. So there are 2 transitions, and what I thought is that so far all the simulations, all the experiments have been done, in that case, the particles, the particles have spherical symmetry. And what I thought, if the particles have a orientational symmetry or an orientational degree of freedom, then would that orientational degree of freedom changes the melting behavior or not? So that's the basic aim. And so first, let's go back a little back. So first, we know that in 2 dimension, there is this impossibility of a perfect translational order. So that means as long as you are at any finite temperature, you do not get any perfect translational order in a 2-dimensional lattice. And then Mermin proved that this perfect translational order is basically destroyed by this finite temperature phonomes, and that's why you do not have any long range order. And then around 1970s, the work by 5 people actually, and 3 of them are here. They got their Nobel Prize in 2016. Because of their theory, we got to know that the melting in 2 dimension is a 2-step process with an intermediate setting phase. Okay, what does that mean? It means that at a very low temperature in 2 dimension, so mostly the arrangement of the particles is hexagonally normal. But there are defects. Even at very low temperature, it doesn't matter how low, but there are defects. And these defects appear in the form of something called dislocation pairs. So one dislocation is a pair of 5 and 7 coordinated particles. So here, perfect order is there, perfect hexagonal order is there. So each particle will have 6 neighbors. But if it is the system is at a finite temperature, then that perfect hexagonal order is destroyed, and the particles sometimes can have 5 or 7 nearest neighbors. So at very low temperature, these 5 and 7 come in pairs. And not only they come in pairs, but rather they come in 2 5 and 7 pairs together. Okay? And then if you increase the temperature, so this is a pair of dislocation. Then these, as you increase the temperature, this dislocation pair gets separated out. And when that happens, you get, so this is a 2D solid phase, this is a 2D hexatic phase, and this is still a hexatic phase. So these pairs are getting separated out. If you increase the temperature more, then this dislocation will be separated into 2 independent 5 and 7 coordinated particles. So they're called disclinations. So very simple. So this is the separation of a dislocation pair. This is one disclination. This is another disclination. Disclination means only 5 or 7 coordinated particles. So our model is this Gay-Burnham potential, which looks like the Lennard-Jones potential, but only this R, the distance between different particles, is now represented by this term. And this term introduces this orientational order of each of the particles, and that's how conceptually this represents some kind of ellipse, elongated ellipse. You can control the length of the ellipse by putting some number in this sigma. Okay, well, I'm not going to detail. Now, what we do is we do molecular dynamic simulation, and we take the help of these package. Again, skipping here. So this LAMMPS package, we put in all the parameters, and then we do run the simulation. What we are looking for, we will change either the temperature or the density of the system, and then we'll look for some order parameter to decide whether it's a solid to the solid phase, hexatic phase, nematic phase, or a liquid state and so on. So we use basically 3 different order parameters. The first one is the radial distribution function, and then this Second one is called the orientational correlation function, which is related to the orientation of the liquid crystalline particles, whether they are all oriented in the same direction or they are randomly oriented. Means this ellipses elongated particles, whether they are elongated or aligned in the same direction or not. So we calculate this quantity. This pair distribution, this will help us to determine whether they are positionally ordered or not. If it is a perfectly hexagonal crystal, you will get to see the very large peaks like that. And if it is a liquid, then you do not see these peaks, but rather like this black line. They get smeared out. And then we also look at the bond orientational correlation. It means that this helps to identify whether you have an acidic phase or not. It's like so if the particle have hexagonal arrangement, G of R, the orientational the pair correlation. And if the particle have their bonds with their nearest neighbor, if that is in order, this quantity helps you to find the line. We'll see some plots next. So first, some snapshots. So we vary the temperature, same density. What happens is at very low temperature, you get to see mostly the green color. What I just did is I colored each of the particles depending on how many nearest neighbors they have. So here mostly green color, that means green means 6 nearest neighbors. If you have red and other color like red and blue, so 7 and 5, 6 green, 8 yellow, and so on, right? So mostly green means mostly hexagonal order. So 2D liquid, 2D solid phase, solid phase, solid phase, solid phase. Something happens. So that's like an acidic phase. Then this is a pneumatic phase. So completely positional order is gone, and these are happening at higher temperatures. So the snapshots gives you some identity, some help to find to see whether you are seeing some phase transition. And this is some zoom in pictures, and then you can also calculate what is the fraction of the particles having how many nearest neighbors they have. So if you are at a low temperature, mostly it's green, means mostly you are at a in solid phase. And as you increase the temperature, so this horizontal axis is temperature, as you increase the temperature, this one goes down, so you see the melting. And these are the orientation of each of the particles. So if you are at low temperature, mostly all of them are oriented in the same direction. And as you increase the temperature, they get randomized. So here solid, here pneumatic phase, meaning these are orientationally. This is still a pneumatic phase, so you still have some orientation. The particles are a little bit oriented, so pneumatic phase, still not liquid phase. And these are the 3 different correlation functions that helps you to determine. So this one helps you to determine whether the solid phase is there. This one helps you to determine whether the hexatic phase is there, and this one determines whether you have pneumatic, meaning liquid crystalline order is there or not. So what is going on here is that this G6, the bond orientational order, if all the particles are oriented with their bonds nicely, at hexagonal arrangement, then this order function should stay horizontal. And that's what happens at these temperatures. So you have 2D liquid, 2D crystals. But then there is a slope. So this curve represents this blue line. The 0.8, this is going at a slope. And remember, this is log scales. So this represents that the G6, which is the bond orientation order, is decaying algebraically. And that's why we say that this blue one is hexatic phase, but then later on, these are exponential decays, so they are pneumatic phase. Orientation, all of them are horizontal, so they all have nice, beautiful orientation order. All the ellipses are directed in the same direction. And this one, the GR, so you see for some of the temperature, there is a large oscillation in the peaks. So to identify which one is liquid, which one is solid, we treat them to whether it's going to some algebraic decay or exponential decay. Exponential decay, no positional order. Algebraic decay, positional order. And then you can from these graphs you can identify which one is solid, which one is not solid. And then you can make some table, and I'm skipping this part, and you can find out some phase diagrams where in the horizontal axis you have rho, the density, the vertical axis you have the temperature, and in this case, what we have solid at very low temperature, then you increase the temperature, you pass through some phase called hexatic phase, pneumatic phase. So the theory that was given in around 70s, the theory still is valid for liquid crystalline materials too. That's the conclusion because of the existence of this hexatic phase at some finite temperature and density. So I am done. Thank you very much.
So it was confused that the lowest temperature is what you're calling the solid.
Yeah.
Is orientations of the nearest neighbor God. They are what do they do in the lowest phase? Lowest temperature phase. What are the orientations of the nearest neighbor gods?
So
That order parameter you define.
this one,
The nearest neighbor bond orientation.
this black line, that's horizontal line.
So it goes to a non-zero constant with a correlation function at large.
Yeah. So it doesn't
Long range
decay. So
Yeah.
it remains horizontal. It doesn't
It's
decay.
a long range order.
Yeah.
And then in the hexatic phase, it's decaying as a power loss.
Yes. So that's a quasi.
But is there any tuning parameter in your potential that can make that transition happen as a first order transition without the power law base?
Yes, in principle, yes, but I have not tried.
Okay.
There is at the very beginning, I gave you that sigma. There are some tuning parameters. You can change the elongation of the particles, and people believe that if you take very long liquid crystals, then this hexatic phase will improve.
So that there be a first order transition.
Yeah.
Order to this one.
Yeah.
For the orientation.
Yeah.
When you showed the melting and the first two diagrams seem to have string of the
Yeah.
So, what are they called, these strings, and I'm unfamiliar with this.
So this is basically the two large domains, and because of the periodic boundary condition, the strings as they grow, because at very low temperature, these dislocations cannot separate. So if they come,
So is it a chain of 5757?
Yes, yes.
Oh, okay.
Any more questions?
Is there an order for?
Yeah.
Is there an order for which is hard to distinguish between one phase to the other? I mean, otherwise it's just pictorially, it is not really clear.
No.
That
So
actually there
this
is an
one,
hexatic phase. So your temperature is like 0.4 and 0.8 and 1.2. I mean,
yeah.
is there
I
a-
understand it. So the answer to that question is to identify where exactly the phase temperature transition is happening. In the theory, there is something called the elastic constant. So you can measure the elastic constants of the system, and at the melting temperature, meaning at the temperature at which the 2D solid melts into an acidic phase, this elastic constant goes to 0. So if you calculate as a function of temperature, that's what we are doing now. Thank you.
Let's start the speaker. Alex and Paul will go to the station. Now we break for tea and we'll be back at 11. This couple of announcement. This is short and tea break. And at the end of the next session, around 1 p.m., there will be a group photo. Okay, and today we will all go down to the lawn. We will guide you, and a group photo will be taken. And last thing is today at 4, the last session ends at 4. There will be a tea, coffee outside, and after that, we have a museum of archives where some of old letters from SN, Professor SN Bose and those things are kept. So that museum will be open from 4. So you are welcome to know that.
কলকাতা স্ট্যাটিস্টিক্স কলকাতা ফার্স্ট একদম প্রথমটা হ্যাঁ ওটা কি কম্পিউটারে নিয়ে নেবেন ঠিক আছে ঠিক আছে নামটা চেঞ্জ করে দেবেন
First one?
This one, long range. This one is in the liquid. Both. Yeah. Very good. So this is the hybrid. Exactly. Then low temperature. This is for all the yeah. Yeah. It's not a local order file. This one. If they were very good. So this is the standard scenario. So now this is going to
So this is happening always. What I'm doing is going to do the effect of our now, so yeah, because this has to be always continuous. What happens is
yeah. This is the unbiased.
because the hexatic phase comes when the pairs are unbound, and so the transition from here to here has to happen.
So this is like a
Yeah, you have to have this 3 pairs. And if
so this one is key.
one is always.
And the question is what is
And this one can be very, very soft potatoes. And then it becomes,
what kind of
it's also cake.
another?
Yeah, it's another
Exactly.
page.
Exactly.
One.
It's already joined.
It
Join
becomes.
So that actually is nice.
Just share করে দিই।
About this. This is like the.
ল্যাপটপের সাউন্ড অফ আছে?
Like real space modeling. Power block.
Allow to share window. Allow to share window, yes. Screen.
So, you know, if I don't worry about this,
Yes.
and I just look at this,
Yes.
then I would imagine that this one is like a TP from the cosine phi.
Subhabat,
cosine
এটা দাও।
phi.
Okay.
And
PDF
this one is like
পেজটা
reflects this order. It is like the
Yes.
right? So this makes sense. So I guess my question was a different one.
You said it.
When choose parameter or different kind of class of parameter. This page, so I don't worry about this. It has to be like
সেটা করে দিচ্ছি।
power law is not exponential.
Yes,
Right?
exactly.
Real thing is, so that's not right. I'm asking about this one.
Yeah.
Is there some soft potential that this disappears? And I go from here to here.
আর
As a
পয়েন্টার
function of
এখান
image.
থেকে
That's-
আমি আরেকটা পয়েন্টার আপনার তো ইউএসবি নেই না আমি কানেক্ট করে নিচ্ছি আমি আপনাকে আরেকটা পয়েন্টার দিয়ে দেবো
Right.
ওকে
So I was just trying to grasp the potential for a tuner parameter.
এই পয়েন্টারটা দাও না আমি চেক করে নিই
And then I get lost.
স্টপ শেয়ার করবো নাকি ওই যে পয়েন্টার উপরে হ্যাঁ স্টপ শেয়ারিং করবো হয়ে গেছে স্টপ শেয়ারিং হয়ে গেছে ঠিক আছে আচ্ছা এটা জাস্ট আপনি জয়েন করেছেন বলে দেখেন ওকে
And then they show why this would be forced to text this space
Yeah.
because this coordination theory comes when then
just presentation having
but
check
then
for share
it's like they look
Okay.
at all this range of differences and they say that if you have a system that is not the exists.
There's no first order. I mean, there's no microscopic model that is
Which make it attractive. It exists. As far as what surprised me is that it says that it's not.
আমি তাহলে জাস্ট পয়েন্টার পয়েন্টার লেজার রাখুন আর এখানে রাখবেন
This transition, like,
Yeah.
nature
Yeah.
changes the length.
Yeah, so he's adding an extra element. This is all for particles that are, yeah, with an extra unit. Yes. Because, you know, in the spin analog, I've been interested in how this space disappears as you change some the other range aspects of the spin analog.
Yeah.
Like clock.
There is,
So that's something we've looked at. So in clock models, there's two ways in which this is exactly. You take a 6-state clock model. Two ways in which you can tune some further range coupling. This exactly. One is that this exactly switches off.
so you have like an expert.
Yeah, 6-state clock, and you can do description of this 6-state clock. 6-volt symmetry. Power loss. But doesn't matter square like anything, but theta can only take values by n by 6. Right? The 6-state clock, that's the speed. There's some tuning parameter for each branch. As a function of temperature. Get this heat. Which pinches off and then. So this is one way. And then there's another way.
Like,
So there's a toy model one. Yeah, you can do that.
Because you can, so for example, Cardi footprint.
You can be fine.
But the problem is getting the analog of this in a microscopic spin. So that we managed to numerically find. But there's another possibility which we have not been able to find a numerically, which is see, this is 6-volt symmetric. Of 6 is 3 2. So you can first break the 3-fold order, then the 2-fold. This will be 3-state orders. Wait. I've seen some. So you think of these 6 states as being made up of a 3-state chords times a 2-state ice.
Okay.
Like this. Or 6-state X. 36 directions. Whether you're here, here, or here, versus there, or there, the icing. And then within each group, is the pots. So you could melt one part on the other and then melt. This is also a consistent possibility in the clock. But we haven't found a microscopic model. So we found a target multiplication point, but not. And so I've been curious whether there are particle systems where similar things like using potential and asking. Probably not. Yeah, but maybe it's expecting freedom. And I don't. Yeah. Oh, but I think that it reminded me of this issue.
If you, I will ask you later again, like, entry on the.
Sure, I'll do that.
But what?
This is some version of the I will actually publish it. You put that. Yeah.
So let's start this session. Our next speaker is Onikan Shai from IIT Bombay, and he will talk about rod-like proteins on membranes, shapes and patterns.
Good morning. I would first like to thank organizers, Una, Shakuntala, Anandamohan, and PK, of course, for giving me this opportunity to talk. So it's slightly change of subject, although it is continuation of liquid crystal. I mean, the job is made little easier by Devabrata, and yesterday Takeuchi also gave some nice introduction. Okay, so I'll jump into the thing. Before that, this is just a one slide advertisement of what we do, mostly for students and postdocs. So we work on membrane physics, liquid crystals, reaction diffusion systems, and recent found interesting active matter in the context of cell division. So today I will mainly focus on membrane physics, interaction between membrane and liquid crystals. Okay. So before I forget, these are the students who have worked on this project. I mean, this sort of things for a while. He's a postdoc now at ISC. Sopusaji is still with us, and Ramakrishna is the person who actually provided us a very basic code for this simulation. He comes from Sunil Kumar's group in IIT Madras. Okay, so this is the outline. So I'll talk about membranes, continuum mechanics of membrane. And once you see the phenomena, you will see that it's an interaction between membranes and proteins. And these proteins are modeled as liquid crystals, simple rod-like objects. And how their interaction gives you different shapes and patterns. Okay. So I got interested in this problem quite some time back, 2009. So in this experiment, they had a vesicle, phospholipid vesicle. And on the vesicle, they had put certain proteins. This is the name of the protein, which is important in bacterial context. So this protein has a property that it has an intrinsic curvature. It doesn't want to be straight. Okay, so once this is put on this membrane and a lot of ATP in the medium, they found a lot of tubes growing. So the question was that why is that happening? Why is the membrane giving rise to these tubes? As well as what is the orientation of these proteins on this vesicle? There are lots of these proteins in the medium. So what was surprising at that point was that normally these membrane tubes are known in biological context. They are very common. But typically, what these proteins do is they wrap around and they force their radius of curvature on the tube, and that's what, I mean, on the membrane. That's why these tubes come. So they are happy on this small radius. That's why these tubes emerge. But in this context, the arrangement was like this. Although the proteins had some intrinsic curvature, but the arrangement was like this. So these are the scales. This is the vesicle diameter, and these are the. Huh? Sorry, where? So these are in seconds. Yeah. So one important thing is that this phenomena is driven by GTP, in the sense that if you do not keep on supplying these molecules in the medium, then these tubes will shrink. Yeah.
50 has more figures and 20 has less, and 21 is more positive.
Sorry. Okay. So these are different samples.
Different.
Yeah. Yeah. Sorry. And okay. So and the interesting thing was they could see tubes. I mean, by engineering how they put the protein on the surface, they could see tubes going outward. So this is a cross-sectional view, and this is a surface view. The tubes come out from these bright spots. So they could see tubes coming out, as well as in another context, tubes going in. Okay. So this is a schematic. So you have a vesicle like this. It may go into this structure or this structure, depending on how you put the proteins on the vesicle. Okay. So that detail I will not go. So basically, these proteins are curved, and you can put them in a way so that they develop concavity or convexity. Okay. So yeah. So we wanted to know how this is happening, and also if you look at this picture, you will see. So this is a sphere, almost a sphere. There is a bright spot is surrounded by 5 some places, 6 mostly, and 7 in some places. So it's not, bright spots are not really random. Okay, so so essentially it has some connection to the fact that soccer balls have not only hexagons, they have to have some minimal number of pentagons in order to close them. So minimal soccer ball have 12 pentagons and 20 hexagons. And it just turns out this object also has that, but in a slightly different way. You have to look into the pentagons and you have to identify them. Okay, so this is the model now. And this is a very general description of the model, and I will show you, other than the particular experiment that I showed you, I will show you some other applications also, which we did later. So generally membranes, they are governed by the phospholipid membranes, they are governed by the bending rigidity. Okay, so these are very familiar Hamiltonian energy of the membrane. So at every point, there are 2 principal curvatures, C1 and C2, and this object is the asymptotal of that. And so this is the bending modulus for the membrane, and this is the modulus of. So this term is called Gaussian curvature, C1 into C2. So C1 and C2 are principal curvatures. And they happen to be the 2 eigenvalues of this curvature matrix. N is the surface normal. And of course, if the surface is arbitrarily curved, these values keep on changing over the space. Okay. Yeah.
C1, C2 square has it already a term. C1, C2.
Yeah.
Why do we
But what? Yeah. So why do I need that? Because the coefficients also matter. See, if I just have that, then they have very specific coefficients. But it turns out, okay. What it turns out is that if you take a closed membrane, then this term completely gives you 0. If you integrate this over the area of a closed membrane, it's called Gauss-Bonnet theorem. And we will be actually mostly concerned with closed membranes. Okay, so there is another way of looking into it, is that any such energy function should be invariant with respect to choice of your frame. So you can use only a trace or determinant of these matrices. So hence, the same thing can be rewritten like this. Okay. So now, and the square is because you don't want to distinguish between concave versus convex. Okay. I mean, if you don't want to do that, then you should have this square term, which is invariant with respect to whether the sign of C1, C2. When you have this or that, the signs may change. So in order to neutralize that, you have the square. But if you have a membrane which wants to curve in one way and not the other, then you have to break this up-down symmetry, and this term comes in, which is often called intrinsic curvature. So the system would like to minimize this. This is anyway not there because I will be bothered about only closed membranes. Okay. So now the question is, the shape that I am showing you, how do you get that? Because of the interaction with the protein molecules. Okay. So this is the model. So I have a triangulated surface, and on that surface at every vertex, I put these rods. So there are three things. One is that I have a closed membrane, and second is that, so everything should be describable in terms of this curvature field, which you can define at every vertex. There is a numerical way of discretely calculating that, and the nematic director field. So this is a new term here. So these rods are described by these nematic vectors. There is no head and tail for these rods. And so the question is how the rods interact with the membrane and among themselves. Okay, so on the vertices.
Because on the left, way more vertices and just on some vertex, decide the density of the rod, and then you use this.
No, or okay, I can choose to put them on fraction of vertices, but in this particular simulation which I'm describing, I have put them on all vertices. So it's uniformly covered. You mean here? You mean here?
Yeah.
No. That is just a visual artifact. It is there. It's a sphere covered with these triangles. Okay, so this is the new modified interaction energy. What it does, what is saying? So this term is the membrane rod, if you like, interaction, and this term is nematic interaction. You will see that I have a continuous thing here and a discrete thing here, but of course, when I do the simulation, this has to be discretized on every vertex. Okay, so here, instead of a simple isotropic curvature term, what I have is that at every point, there is a C1 and C2, that is the principal direction of curvatures. But the rod is, okay, first of all, the rod is always tangential to the surface. They are sitting on the surface, okay? So according to its direction, this is the blue direction of the rod. These two principal eigenvectors, along which I have C1 and C2, I want to find out what is the curvature along the rod and perpendicular to the rod. So along the rod is this thing, H parallel, and this is H perpendicular. So this is, and there are two intrinsic curvatures, one for along the rod, the other for perpendicular to the rod. Now, why is this? Now, if you have a protein which is bent, then you would presume that the membrane which is underneath would also, the protein will force it to bend in that direction. Okay, so that's why this term favors that wherever is the rod orientation, the rod is tries to give a curvature on the surface. But this term looks completely ad hoc at this point, that I have the rod, why perpendicular to the rod there should be a intrinsic curvature. Okay, but actually what I will show you is that it is a story about this term, which was completely not thought important in the early publications of Sunil Kumar's group. Okay, and this term is a nematic-nematic interaction. What it tries to do is just to make the rods parallel to each other. Okay, which it would anyway do whether there was membrane or not. Okay, so now these two terms look little ad hoc, but these extra things, H parallel, H perpendicular, you can express them as traces. So now they are a little more complicated because so you have the curvature matrix, you have the nematic director. So there are some quadratic combination of those. So these terms also are invariant with respect to frame rotation. And this gamma is the Lewis beta in 2D. Okay, so with all this, when you do the simulation, Monte Carlo simulation, completely equilibrium, without taking into fact that GTP, so I assume there is a lot of GTP already there in the medium. So this, although see the phenomena is actually a non-equilibrium phenomenon, okay, but because of our limitations at that time we did it in an equilibrium way, and we find these tubes, okay, and you will see the arrangement of the rods on the tubes. They are not azimuthal, but they are parallel, okay. So what's happening is that because of this sort of terms, there is an imposed curvature perpendicular to the rod. So if you look at this picture, let's say these are rods, and if I impose a curvature perpendicular to it, so around the tubes, this is the arrangement of the rods. So the interpretation of that is that, so in the actual experiment, what happens is that these rods bundle. So bundle meaning they're longitudinally oriented and they actually touch each other and so on. Of course, in our simulation, we cannot do that, but this is a poor man's way to mimic bundling. Okay. So, and there are many examples in biology where, for example, beneath the cell, certain proteins like actin and others, they can form bundle and push out membrane protrusions in the tube form like this. Okay. So this is basically a mimicry of that. Here the context is different. The proteins are on the outside and they can form bundle. They have lateral attraction between them and so on. So the second term is the key thing which we interpreted in this way. And we can also show that if you turn the signs of this, you can have tubes going inside. Okay. And that is quite consistent with what they do in experiment.
You can accept now, because if you have a Hamiltonian like that.
Yeah, no, but see the Hamiltonian, the sign of that matters. Yes.
The sign that will matter.
Yeah.
The minimum is at C perpendicular.
Yes.
One is positive, one is negative, you have a different kind of curvature.
Yes.
By minimizing energy.
Yes.
Negative.
Sure. Sure. So, but what will happen is, so C positive, negative meaning concave or convex. Okay. Yeah. 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 It is. Once you have this, the other one is obvious. Okay. Now, what is interesting here is the arrangement of these tubes on the surface. Now, here comes a little bit of notion of defects of liquid crystals. So the rod-like molecules, they can form in various ways, and they are characterized by this topological charge. And accordingly, you can have S1, S-1, and so on, different type of defects. And there is a theorem which goes by, often popularly goes as hairy ball theorem, more formally Poincare's index theorem, which tells you that if you have a surface, closed surface, then the total amount of topological charge is 2 minus g. So in this case, g is 0, so it has to be 2. Okay, total charge is 2. Now that works out, of course, that's a theorem, it has to work out. This is a closed surface in a very nice way. Although here you have large number of defects. For example, you see these red circles are locations of minus half defects. These points where the tube comes out from, they are +1 defect. But you can show very nicely that the total charge works out to be 2. And there are exactly 12 pentagons and 20 hexagons. That depends on your area. If you take bigger area and keep the scale C1, C parallel perpendicular same, then you will have many more, but still the total charge will work out to be 2. Okay. So, okay, so let me not go into this statement here. Okay, so it has some connection to soccer structure. So using this same formalism or the same model Hamiltonian, we had recently used it for some other protein on a membrane. This is not on a membrane, but inside a membrane, a different protein called septin, which is important for cell division and so on. So there they find some other kind of structures, and we do get those more or less. And we also predict a phase diagram. So these are the experimental ones. So in this regime, one can explore other structures. So these are recent collaboration with this QD Institute group. Okay, now this is the last thing I wanted to mention. This is our most recent thing. That is, there had been a Nature Physics paper. It created a lot of waves about how does these tentacles form in Hydra. Hydra is a very small organism, mostly lives in water. So what they showed, because of experimental improvement, they could see that a lot of actin fibers here aligned in specific way, and they had sort of rationalized this as, I mean, from the direction of the fibers, that there is a +1 defect here, and so every tentacle has a +1 defect. This one is the central place, which they call it a mouth, where the Hydra apparently maintains a +1 defect by some mechanism. Together, everything works out to be +2 because it's again a closed surface, same tone. So, okay, now because active matter is so sort of popular these days, they tried to project this as, or they did project this phenomena as a active matter phenomena where ATP is involved and so on. But what we think is that actually the activity is not, there is no evidence of activity in terms of flows, because in active matter physics, what happens mainly is that you have activity, and you have activity induces flow, and flow moves things and shape changes and so on. In this context, there is no such evidence. Rather, there is these tentacles, they actually grow, meaning so initially it would be a cylindrical kind of object, and then the tentacles grow and the fibers also grow into them and so on. And also in this phenomena, which these people completely ignored, is that there is a chemical called beta-catenin, which people have documented long time, that where the tentacles form, there is a surplus of these chemicals. So it is not really just a this defect-driven thing as they try to project it and active matter in terms of actin. So also these actins are very long fibers here. They are not really small rod-like ones. So, okay, so we just thought of looking at this problem in our way. So we started from a cylinder, and we increased chemical, so to say, some chemical concentration here, which all that it does is it generates a C perpendicular non-zero in this zone and 0 here. Okay, and but now we don't do an equilibrium simulation. So okay, so we have first done an equilibrium simulation. What we found is that despite the claim that this +1 defect is essential here for this structure, we found that that's not the case. In fact, there are two types of +1 defects possible: these Astor-like or these polar types. Or you may have, so in either of the cases, or even if you have no defect, still if this chemical concentration of certain chemical is high here, which in our language is C perpendicular, you will have tubes. Okay, so this +1 defect driving the whole process, we don't think that is at least physically tenable. Okay, biologically there could be some reason, but it is not essential from physics point of view. And then we plunged into a non-equilibrium simulation of membranes, which is still, different people have different ways of doing it. It's still not a settled area. So here, all that we did was that instead of a Monte Carlo simulation, we introduced in our moves some detail balance breaking terms and do the simulation. And so what we do is, first we decide that out of all these vertices, there are certain fraction where these actin polymerization is taking place. In fact, okay, in case of this Hydra, these things happen because of these actin fibers aligning here. Okay. So we try to keep a global concentration of these polymers. So certain fraction of vertices has this and certain others don't have this. We try to maintain a global ratio, but there is some local moves also which breaks the detail balance that so as a together this system does not actually adhere to what we try to constrain, that is if only certain fraction will have this C perpendicular non-zero. So, but what we verified is that if you change this ratio, more or less, I mean, when you reach sort of a, I mean, when the tubes start to grow, these vertices tend to accumulate together, and from there the growth takes place. And the ratio is not exactly linear, but it is a monotonic function of what you impose. Okay. So yeah. So, but the main point. Okay. So one point I want to emphasize here is that whether you do a equilibrium or a non-equilibrium simulation, this tube growth is not really so much of activity driven. The simple reason is the following: that in all the active matter phenomena that you hear about, there is also an energy function, although the energy or free energy does not tell you what the steady state will be, because you don't have it's a non-equilibrium system. But it very often it is that the energy has a role, and then you have role of some non-equilibrium forcing term or activity or whatever. Okay. So you will see some signature of the underlying energetics also, although that does not completely settle the system because it's a non-equilibrium system. Okay, so that's the conclusion I come to. That is the elasticity, and then so the energetics of the rods and the membranes, they have a large say in how the system will finally look like. Role of activity is somewhat unclear, although we have done a non-equilibrium simulation in this case. And about this defect dynamics, you will also hear that defects drive things, but it seems to us that quite often that's not the case. Defects are there because of all the stresses and strain conspire in a way, and you are let's say in 2D surface, so there are constraints of these theorems, topological theorems. Because of that, the defects emerge. And where defects emerge, you may see things happening in the sense that you may see that some growth is taking place and so on. But according to us, that's often not the driving force. So defect dynamics is important. They give you nice pattern. They help you to rationalize structures, etc. But they are not always the driving force. Okay, I end here. Thank you.
Any questions?
Yeah.
So in the equilibrium simulations, I guess is it basically just energy minimization, or the
Yes.
noise is not so important? Right?
Only energy minimization.
It's just energy
Yes.
minimization. In that sense, probably the activity becomes important. If the noise was important, then maybe.
Yes, if you drive the activity very strong, then it may be important. But for this kind of phenomena, it is a side role. Yes, yes.
The other question was like in your the pattern that you show is the number of like the bigger structure, the number of pentagons is always pentagons and hexagons.
Yes, but the number scales with the size. So it is discrete. So after this 12, 20 is the minimal structure. So if you go to higher volume, so they will scale.
But I think
Pentagons always have to be there. You cannot complete the thing without. Yes. Yeah.
Any other questions?
Yes. Actually, yeah, I'll tell you. It's a vesicle with regular shape, but so the left figure you mean? Yeah. So actually, we hold the volume constraint. It looks like a sphere, but we allow some excess area. So let's say I take a sphere and then I impose. I don't hold the radius of the sphere to be fixed but I hold the volume fixed. Okay, and that volume is little smaller than this, smaller than that of sphere. Otherwise, it cannot, because sphere is the minimum, minimum surface area.
My question is like, if you start with initial condition with some irregular vesicle,
Yes.
that's a more practical scenario.
Yes, still it will go to that. That we have
Okay.
checked. Yeah.
And the other question is, in your simulation, you were assuming it's a thermodynamic equilibrium, but you say that there are GTPs involved. in it.
Yes, yes.
So if you include some energy conversion
okay.
there, like what will
Yeah,
happen?
so in our way, GTP comes in the following way. See, what the GTP does is that impose these proteins to become curved. So when you take off these things, these fuel molecules, then it becomes its curvature changes. The protein's curvature changes. So it can no more drive the. It can no more impose curvature on the membrane. So that would be setting this C parallel and C perpendicular to be 0. So then all these tubes will shrink or some smaller value. Yeah.
So, what was the experimental system that you showed?
The first